Let's explore KVL in an AC circuit. First, we can recall that Kirchhoff's voltage law suggests that the sum of all the potential rises and falls around a closed loop is equal to zero. Here we have KVL working in a simple DC circuit with 3 resistors and 3 voltage drops. The equation for KVL can be written as this: the supply voltage E minus the voltage drops V1, V2 and V3 equaling to 0. We can rearrange this formula so that we can find the supply potential when we know the separate voltage drops. I can tell you now that this process in KVL itself works in an AC circuit. This particular rearrangement shown next to the arrow is how we will explore KVL in an AC circuit to help us solve the question of finding the supply voltage. Here we have a simple AC circuit which we need to calculate the value of the supply voltage. The blue and pink rectangles represent a certain circuit elements that create their own voltage drops. The blue being VA as 50 sine 283t plus 30 degrees and the pink as VB of 30 sine 283t plus 60 degrees. Using KVL, we can successfully find a value of E in. The difficulty in this compared to a DC analysis is working with polar phasor and rectangular forms in order to be able to generate an answer. Because we are performing operations with addition and subtraction on the next few slides, everything has to be converted to rectangular form to allow for this. Firstly, for VA, we know the polar form, hence we can easily convert this to phasor form by taking out the amplitude at the front and the angle within the brackets. Then we get 50 angle 30 degrees. We can convert this phasor form to rectangular easily on a calculator. After plugging in the numbers, we get an X value of 43.3 and a Y value of 25. To write this in rectangular form, it is there, VA is in the presentation. Now for VB, again we've been given the polar form. Changing to phasor form we get 30 with an angle of positive 60 degrees. The next step involves calculating the x component as 15 and the y component of 26, which then gives the rectangular form as here, VB equals 15 plus j of 26. So from before, we know that to calculate E in, it is found by E in equals VA plus VB. The answers here in rectangular form can be subbed easily into this equation. Therefore, we have E in equals 43.3 plus j of 25 plus 15 plus j of 26. Addition is carried out with the x and y values separately. We then derive E as being 58.3 plus j of 51. Using the calculator, we convert this rectangular form back into a phasor form, getting a value of R as 77.5 and the angle is 41.2 degrees. This can be easily put back into the polar equation as the same format of the question itself by using 77.5 as the amplitude at the front, then sine, the same 283t, and then the angle inside the brackets is 41.2 degrees. We can quickly confirm Kirchhoff's voltage law here. Knowing that E in minus VA minus VB should equal to 0, we can try and prove it. Following along here, where the phasor forms have been changed into rectangular form, we can minus the x's from the x's and the y's from the y's. This then results in 0 plus j of 0, which equals 0, and confirms KVL.